All right, so if you need to pause, read. Other than that, this particular problem is just a static equilibrium problem when you have a block that is sitting on a rough surface and it's not allowed to move. The coefficient of friction here is 0.045 given in the wording. The mass here is 10 kilogram. The mass of the hanging object here is unknown. It wants us to do a couple of tasks, draw the free body diagram, and then calculate the mass of the hanging block here. All right, so let's go ahead and do part A. To do part A, just draw your forces out, identify what's present and what's not present. So here in this diagram, I notice there are 3 strings. Here's 1, here's 2, here's 3. So in no particular order, I'm just gonna label my subscripts. You label your subscripts however you want, as long as you keep up with your own work. All right, so I'm gonna call this string 1. I'm gonna call this second diagonal string here string 2. So I'm just gonna do a little clockwise, and then there's this third string that's vertically. I'm just gonna call that T3. Okay. So in order to draw the free body diagram, all you have to do is identify your forces and then just use the actual vectors and not the components. So here, I'm just going to draw out the weight of the 10 kilogram block that is resting on the surface of the table. Because it is sitting on a surface, there is a contact force exerted by the surface onto the block. So that's going to be F of N. And then because it's not moving, if it were to move, it would move rightward. Because T1 would be pulling it right. However, it's not moving, so there is an opposing force because the problem says that there is static friction. So I'm going to draw static friction pointing leftward because it opposes the movement of the block if it were to move. Okay, so I'm going to call that Fs. Here's T1. In each string, I'm just going to draw it 2 arrows, one pointing right, one pointing left, based on the junction here. All right, so T1, there's an arrow pointing right if your perspective is for the 10 kilogram block, because that would be the force that's causing it to move to the right if it were to move. And then, okay, and then the next one I'm going to draw is drawing left. Again, in each string, there's an opposite and equal because this particular junction in the center is not allowed to move. So there's a force pulling it left, a force pulling it right. So therefore, this string, there are 2 arrows equal in magnitude but opposite in direction. Both are called T1. And then T2 is going to be pointing towards the ring where it's being held. So that's that. And I'm going to go ahead and draw the components out for T2. T2 is pointing in the northeast direction, or I like to think of it right and up. So my T2x is going to be pointing right. And this is 30 degrees. So therefore, the cursor, where my cursor is tracing back and forth, that is also 30 degrees. And because this line touches that angle, it is your adjacent. And if it's your adjacent, it would be cosine. So T2x would just be T2 cosine of 30. And then this is your opposite. Okay, once again, this is 30 degrees. So this is your opposite leg, and that is in the y direction. So T2y would be T2 sine of 30. It's sine because it is the opposite relative to the angle given in the diagram. Okay. Other than that, let's go ahead and draw out T3. T3 is what's keeping the hanging block stationary, but it's also going to be keeping this little knot in the center here stationary as well. All right, and then I'm just gonna go ahead and draw out the weight of the hanging block. Here I'm just gonna call it W. I already use F of G over here, and I don't want to use F of G1 or F of G2, so I'm gonna call it F of G and W. It's up to you. You can call this F of G1, F of G2, but I'm just gonna call it F of G and W. Okay. All right. So to draw the free body diagram for the 10 kilogram block, so I'll go from left to right here. All you have to do is just really just redraw your diagram with just the vectors touching the dot. All right. So here is the weight. F of G, here's F of N, those are equal in magnitude. I did my best to draw stuff to scale for you. And then here's F of N, right? And this is T1. And then against T1 would be F of static. And those two have to equal in magnitude in order for the 10 kilogram block to stay stationary. So when technicality comes in, try to draw your stuff, draw on a scale, on scratch paper, you do whatever you want. All right. Let's go ahead and draw the free body diagram for this hanging block. As you can see here, this hanging block only has 2 arrows touching it, the weight of the hanging block itself, and then T3, which is the tension that is holding it up. So I'm just gonna go ahead and just draw that out. Here's the weight of the hanging block, and here's T3. Once again, these two vectors should equal in magnitude just because it's not moving. All right, that's it for part A. Let's go ahead and do part B. Part B asks us to find the mass of the hanging block. Well, to find the mass of the hanging block, the diagram didn't give me what this is, so I'm just going to call that capital M. Why not? Okay, you can call it lowercase m, whatever you want. I'm just going to call it capital M, so let's go ahead and find capital M in my work. To do that, I'm just going to focus my attention on this particular hanging block. So you notice here I cropped out this free body diagram, which is what I've drawn here for you in part A. So I'm just going to set that up, make a bunch of true statements, and your work should be okay. So the first true statement I want to make is that the weight, the magnitude of the weight of the block is equal to the tension that's holding it up, right? So in this case, I can say F of G, or simply just mass times G, is equal to T3. Well, I'm trying to solve for M, so I'm just going to go ahead and do algebra first. I'm just going to go ahead and divide both sides by G just to isolate for M. So here, in order to solve for M, I need T3 and G. Well, G is easy. G is just 9.8 since, we're on Earth and all that. But I need T3. Well, I don't know what T3 is. However, if you look at this junction here, watch where my cursor is, right? There's a little ring here, it's not moving. Well, there's T3 pulling it down. In order for it not to move, there has to be an opposing force pulling it up. Well, if you look at T2, there is a T2Y pulling it up. So T2Y's component can be drawn over here if you like. Watch my cursor, right? So if you want, you can move that T2Y over here, which implies that there's a T3 pulling down and a T2Y pulling up. So therefore, I can replace T3 with another true statement, and that is T2Y. So T3 is pulling it down, T2Y is keeping it up. They are equal because nothing is moving. Now, I can break up T2Y into its statement. Earlier, I stated that T2Y is T2 sine theta, or sine of 30 here, because the diagram gives us the angle touching the x-axis, and T2Y is the opposite, so a sine. So I can substitute out T2Y for a true statement, that is T2, the hypotenuse, times sine of 30. As you can see here, sine of 30 is just a number, it's just a half. G, once again, is 9.8. The only thing that's kind of holding you back here is T2. You need to find what T2 is in order for you to complete this task, okay? Well, that is it in the x direction, or excuse me, that is it in the y direction really for the hanging block that I'm choosing to look at. So the only thing I gotta do is find T2, so I'm just gonna go ahead and find T2 by focusing my attention on the x direction. All right, so there is a T2x. I've already utilized T2y, so I have T2x that I can kind of mess around with. All right, so let's go ahead and do it. I can make another true statement. The whole entire system is stationary. So if you look here in the center of the diagram, right, this ring is not allowed to move. So therefore, we say T2x, which is pulling right, must equal to T1 that's pulling left. But T1 is pulling this block to the right, but the block is not moving. So we say that T1 is equal to the force of static. So really, I can say that T2x, which is pulling right, equals to T1 that's pointing left, but T1 pointing right equals to F of static pointing left. So this is a true statement. They're all equal in magnitude. So I just want to make sure that you understand this, okay? If you just look at the magnitude, if this is 5, this is also 5. If this is 5, this must also be 5 because everything cancels out. So it's the same number. It's just the arrows are opposite because it's behaving differently based on your perspective or which object you're looking at, okay? All right, so because of that, I need T2 up here. So I'm just gonna go ahead and bypass T1. Why T1 is there, I don't really care for it because I can literally just bypass it and say that T2x, which is the component pointing right, must equal to the force of static acting against the system, okay? So therefore, I can just say that T2x equals to F of S, okay? I can just bypass this middle guy. This middle man right here in red, I can just bypass because there's an arrow pointing right, there's an arrow pointing left, oh, cancel, okay? All right, therefore, I can substitute out T2x for T2 cosine of 30, which is right here in purple. So T2x earlier is cosine because the angle, once again given, is touching the horizontal axis, which is this here is your adjacent, so it's cosine. All right, and then Fs can be substituted out for mu s f of n by definition. And then here, I'm just gonna go ahead and isolate for T2 by dividing both sides by 30, or cosine of 30. I highlighted f of n here because if you look at the box, right, the 10 kilogram block here, which is generating the force of static friction, there's an f of n pointing up. But earlier in the free body diagram, I stated that the f of n must equal to the weight of the block pushing down, right? Because the acceleration in the y direction is 0. So I'm just going to make another substitution out. Instead of f of n, I'm just going to substitute out for f of g. But I highlight this f of g because you're looking at the 10 kilogram block, okay? All right, other than that, you can substitute out f of g for mg because by definition, f of g is just mass times gravity. And as you can see here, you have everything. You know mu s is 0.45. You know the mass of the block sitting on the table is 10 kilogram. G is 9.8, and cosine of 30 again is just a number. So I'm just going to crank that out on my calculator. So 0.45 times 10 times 9.8 divided by 0.866. If you punch in cosine of 30 on your calculator, that is what it's about, 0.866. And if you simplify all that, T2 is going to come out to be about 50.92, right? So now that I know what T2 is, I can just substitute it back in for my original statement when I was looking at the y direction. So in order to solve for m, I'm just going to say T2 is 50.92 because that's what I just calculated, times sine of 30, and then g, I just went ahead and substituted in for 9.8. Other than that, I'm just going to do that, and then you should get about 2.6 kilogram, and that would be your answer for this particular problem. Okay? All right, stay nerdy, don't be wired.